Hello everyone, I'm Indrasish. Today I'll be giving an overview on channel charting. Before we dive into the topic of channel charting, let us discuss the basics of MIMO. Now, here in this figure, we can see there's a MIMO channel consisting of k number of users acting as a transmitter, and there is a single base station with multiple antennas acting as a receiver, and in between there is a wireless MIMO channel. Now this MIMO channel can be represented in baseband as this equation given here, where R is the received vector, S is the transmitted vector from all these users, and this Wn is the noise component, and H is the channel state itself, and N is the discrete time index at which we are gathering this information. Now in channel charting, we are not interested in this input output chain. Rather, we are interested in this channel state information itself, which is Hn. And this Hn is solely determined by the positions of the users, which is like where this mobile users are in a certain environment, and the scatterers or reflectors in the environment, like big trees or buildings, and the base station position or the receiver position. Now for our system model here, these base stations are more or less static, and all these big buildings and trees, they are also kind of static as well. So we can think channel state information as a function of this transmitter positions or user positions, and that's the key idea behind channel charting that we are going to discuss. Now, what motivates us towards channel charting? The primary motivation for channel charting was localization or positioning. Now, if you try to localize some mobile user in a dense urban scenario, it requires a lot of hard work, and you have to know the channel geometry as well. There's a lot of thing going on, and in many cases, there is a huge number of parameter, and the models are quite intractable. So what channel charting does is it takes a data driven approach, which recycles the estimated CSI to extract the transmitter's position from it. Now it has been shown that this CSIs, though high dimensional, but resides on a low dimensional manifold. So the job of channel charting is to learn these lower dimensional manifold structures and spit it out. And it has been shown that this low dimensional manifold structures kind of associate with TX positions, which means, let's say, the CSI for two closely spaced users gives out two pseudo locations which are also close. Now with this, we move on to the pipeline of channel charting. Now the channel charting pipeline first consists of a feature extraction block. Now what are these features that we should extract from the CSI data? Now the common literature takes sometimes time frequency or antenna domain covariance matrix. Some of them takes frequency domain autocorrelation function, and few new literature, they take angle delay power profile as the feature to extract, and they have shown quite good results. Or you can go for machine learning approaches and try to learn the feature itself. Now you extract the features in high dimension, now you have to go to the lower dimension, and that's basically dimensional reduction techniques. Now we can go for linear approaches like PCA, but they don't work very well, and so we generally go for all these non-linear approaches, which are multidimensional scaling, salmon mapping, isomap. Some even use TSNE, but all of them comes with certain drawbacks. So most of the recent literatures, they go for artificial neural network based approaches using autoencoders or Siamese networks. But the problem here is all of these techniques that we have listed here up until now, they solely depend on the Euclidean distances between two features and two locations, let's say. So that's a bad news, and it has been proved in existing literature that it is a bad news. So for that, very recent papers, they try to learn the distance metric itself. They use triplets and all kind of things to learn this distance metric, and with that they do dimensional reduction. And after dimensional reduction, you get this low dimensional pseudo positions, which effectively represents the user locations. Now, how do you say that your dimensional reduction technique is good? Because this whole scenario is kind of problematic. If you see, dimensional reduction that we are doing here is completely unsupervised. So classification accuracy is not valid as a performance metric, and also we don't have any ground truth for low dimensional representations. So all these mean square error minimizations, they also don't work. So existing literature shows two neighbor based measures, which is continuity and trustworthiness. Continuity basically tries to see if certain points k top neighbors in a high dimensional plane are still there in the low dimension space or not, in low dimensional representation or not. And trustworthiness is basically the same thing from the perspective of the lower dimensional thing. Basically, these are all probabilities that I would say that this k top neighbors in higher dimension, basically with how much probability they are present in low dimensional space or not, that is basically continuity. The opposite thing is trustworthiness. And if these quantities are in generally 1, then close to 1, obviously it can't be 1, it would be ideal. If it is close to 1, we can say this method is good. Now there are other performance measures as well, which is k stress and r distance, that has been reported in the existing literature. But the thing is, with all this thing, what's the advantage of it? Of course, the first one is without using any ground truth information, we are getting a pseudolocation. That's good. But what about other things? Because localization is pretty much a well-solved problem. One thing is, it has been shown that with these pseudolocations, you can try to predict future CSIs. If you have some additional information available, you can go for SNR prediction, you can do pilot assignments, you can do even beamforming as well. And with pseudolocation, handover prediction is a very easy task. Our work focuses on this future CSI prediction. Now, in general, what happens if you work with instantaneous CSI, it offers a high accuracy and high system performance, but there's a huge estimation overhead that comes with that. You can use statistical CSI that avoids this overhead, but generally the system performances are kind of degraded. We think of channel charting as an intermediate approach between this. With existing statistics of channel state informations, if we use this channel charting to predict future CSI, we think that we can reach in between these two techniques. So basically that's our work. And with this, I end my overview on channel charting. Thanks for listening.